Hello everyone, my name is Jana Chaaban and I lead the Process and Applications Laboratory at Heidelberg Instruments Nano, based here in Zurich, Switzerland. Thank you all for joining the webinar today. In this talk, I'll be presenting our latest innovation, the next generation NanoFrazor system, which we have released just this year. I'll discuss how this tool is ushering in a new era of thermal scanning probe lithography with a particular emphasis on parallelization and automation. Before we dive in, I'd like to give you a very brief history of our technology. The NanoFrazor technology is a thermal scanning probe lithography technique which originates from the IBM Millipede project, which ran over several years at the IBM research facility in Zurich. The NanoFrazor system has been commercial since 2014, and in 2018, we joined Heidelberg Instruments. At the moment, we are mainly 25 employees based in Zurich, working on both the development and the production of the NanoFrazor technology. And this year, we launched our next generation modular NanoFrazor, which is modular, flexible, and 10 times faster. I will introduce this system to you during this talk. So going back to the NanoFrazor technology principle, this is a direct write thermal scanning probe lithography technique that uses an ultra-sharp heatable silicon tip for both the writing and the reading of nanoscale structures. You can think of using the NanoFrazor whenever you need artificially made nanoscale structures on a surface. And here, because we are using heat from the cantilever tip as a trigger for patterning, we need thermally responsive surfaces below. For example, this can be phase change magnetic materials, or in the most standard of cases, we use a thermal resist called PPA. And this resist is commercially available both from Allresist, a company based in Germany, and also from Polymer Solutions based in the US. In this case, upon contact with the thermal resist PPA, the resist right under the tip readily sublimates, and this is an endothermic decomposition reaction, which means the heat is not uncontrollably spreading on the PPA layer or on the substrate. In addition, we don't need any proximity corrections for this lithography step, and because the PPA is sublimating directly, we don't need an additional development step, as is usually the case for photolithography and e-beam lithography. When it comes to resolutions with writing into PPA, we can reach around 10 to 15 nanometers of lateral resolution and also a single nanometer in vertical resolution. More recently, we have also integrated a laser writing head to our NanoFrazor tools, and this allows for much faster writing on a larger scale. This time we're talking about micrometer resolutions. Here also, the laser writer head operates by directly sublimating the thermal resist. So you could think of using a mix and match lithography, combining an ultra-sharp tip for high-resolution patterning of features and the laser writer head for larger scale features, both using the same material system, PPA. And what is very important for the NanoFrazor principle is that we combine both the reading and the writing, and all of this is done in situ within the same system and with the same cantilever tip. So because of this, we say that we are performing patterning in a closed loop fashion. The way this works is exemplified in the simulated video. The cantilever with the heated tip moves in one direction to remove the resist according to your input layout and design. Then the tip cools down within microseconds to room temperature, and it reads the topography that we have just written. In the background, the software is comparing deviations from the intended design and the read topography, and differences of even a single nanometer can be detected and corrected for the patterning of the subsequent lines. So we have a live feedback to improve the patterning, which is running in the background. This is a simulated video of how this would look like and how the topography image would be built up in the NanoFrazor system. What's really powerful about this technique is that we don't require a separate metrology step after lithography to judge the quality of our written features. On the right-hand side, we see a video which was captured also using a NanoFrazor system by some of our collaborators. At the bottom this time, we see a cross-sectional profile of the target depth going line by line, also in this grayscale example, and also the measured depth and how they both follow each other quite well. So when it comes to grayscale lithography with the NanoFrazor, we can achieve single nanometer accuracy both for discrete type features like these steps that we see here, where each step is about 1.5 nanometer in depth differences. And also when it comes to continuous grayscale features, for example, sine waves, holograms, and also blazed gratings. So this grayscale lithography capability has proven itself to be very useful for photonics applications, and I'll come back to this later as well. Now, if you want to fabricate nano devices, we also need a way of transferring these features from the top resist layer down to our material of interest. And for this, we perform a wide array of pattern transfer steps. And these are all compatible with the semiconductor pattern transfer steps that you're all familiar with from the clean room. For example, if we had a grayscale feature in the top PPA layer, the top PPA layer itself can be acting as a mask. And with a dry etching step, we can transfer these features onto silicon, nitride, or various other oxide-end materials. The same goes for 2D patterns, which are present in the PPA layer. Through dry etching, or also wet etching, we can transfer them downwards to the material of choice. We can also perform additive manufacturing, for example, with metallization and liftoff, or we can also use the PPA features to create master molds that would then be compatible with nano-imprint lithography and higher throughput fabrication. So in this talk, I'll be focusing on the first three pattern transfer methods because these are the ones that we most commonly use in our applications. If you'd like to get a wider view of all the available pattern transfer steps in combination with the NanoFrazor lithography, I invite you to visit this review paper. So going back again to our example of grayscale lithography, here you could see the output of this writing method from the NanoFrazor. On the right-hand side, we have the topography image, which is readily generated from within our NanoFrazor system. And on the left-hand side, we see the SEM image of the final created feature here in silicon and here in silicon nitride for creating faceplates. In both cases, the PPA itself was used as a mask to transfer downwards onto the material of choice. Now, if we take the example of silicon, we can amplify the features from PPA downwards to silicon up to 10 times if we tune the etching recipe properly. If we're looking for an even higher amplification of the features, then you could think of introducing a very thick hard mask layer in between the PPA and the silicon, for example, thermal oxide, and then using a selective etching technique like TRIE, you could amplify these features much more as well. So this method, as I mentioned earlier, has proven to be very useful for nanophotonics devices applications, but also for bioengineering applications, where in one case, we've created 3D channels with 1 nanometer accuracy for the precise sorting of bioparticles and the creation of nanofluidic Brownian motors. In another case, we used the topography of a human tissue and replicated it directly into PPA. And because PPA is biocompatible, we were able to directly culture stem cells on top of the PPA surface. Another pattern transfer technique that we use quite commonly is the bilayer liftoff, which I'm sure you're all familiar with. In this case, we have 2 layers of resist, the PPA on top as usual, and at the bottom a liftoff resist, which can be PMMA, PMMA-MA, PMGI, or any other liftoff resist that you're familiar with from fabrication. The way this works is again starting with a patterning step into the PPA itself. And this time, to transfer the features, we don't use a dry etching step, but rather a wet etching step. Then a evaporation, either to metallize the structures or any other material deposition as well. Then we perform a lift-off step. In the most common of cases, this is done simply with acetone or DMSO, and we recover our final features. Some examples of the bilayer lift-off are shown here, and I'll show more of this also during the next slides in my talk. The limitation of this method is, as you can imagine, the resolution due to the isotropic nature of the wet etch pattern transfer method. So when it comes to high density features, there's a limit beyond which you cannot make these two lines approach each other. And this is because of the isotropic undercut of the underlayer. If we were to make these lines any closer, you could imagine how the top layer would collapse. So with this method, we've been able to reproducibly achieve resolutions when it comes to line and spaces that are in the 100 nanometer range. And for isolated features, this can be a much higher resolution. For specific geometries, for example, bow tie structures, the undercut plays to our favor and allows us to get much narrower gaps than other geometries. In this example, a 14 nanometer gap. What is particularly useful about this technique is that we don't use any dry etching or oxygen plasma step for the pattern transfer. So the bilayer lift-off method is particularly useful when it comes to patterning contacts, for example, on sensitive nanowires or 2D material flakes. And because we're not using a charged beam, we actually operate in a damage-free way using the heatable tip, and we found that with this heatable tip method, we can get much better electrical transport on sensitive materials than with E-beam. And I'll also show you an example of this later on. Now, going back to our liftoff, if we wanted to push the resolution further with the liftoff method, we can do so as well. We just need to modify the resist stack slightly here. In this case, we also need to use a dry etching pattern transfer method so as to maintain the integrity of the features written in the top PPA layer. So the resist stack, in this case, we call it the high resolution resist stack. And what we do is thin down the top PPA layer to allow us to get higher resolution. And also we introduce a silicon dioxide or any other hard mask thin film in between the top PPA layer and the organic transfer liftoff layer underneath. And for the silicon dioxide thin film, if you have access to a dielectric evaporator in your lab, this can be used to create this film, or you could also use a spin-on glass, which we've used in the past as well. It's called pi bond, and it operates similarly to any other polymer resist. You simply spin coat it onto your sample, do a post-apply bake, and then apply a plasma ashing step to solidify the layer. So there are many ways to obtain this thin film hard mask. Once your stack is created, we again launch the patterning by writing on the top PPA layer. In this case, we apply a series of dry etching steps using a reactive ion etcher, RIE, to transfer the patterns downwards. Then we use a directional deposition method, in most cases evaporation, to deposit material on our samples, and again we lift off the entire stack, again either with acetone or DMSO, depending on the organic transfer layer used. And for all these etching recipes, we've combined our know-how over the years in a recipe book that we offer our customers. So when it comes to the high resolution liftoff, this method allows for much higher feature densities, as you can see in these examples here. And when it comes to lines and spaces, we've achieved resolutions of 30 nanometer lines and spaces. And if we are talking about more isolated structures, then we can push this resolution even further to around 20 nanometers. So I've shown you now a brief overview of some of the most commonly used pattern transfer techniques in combination with NanoFrazor writing. But of course, there are also many different ways to use the heated tip of the NanoFrazor. You can again visit this paper to get a better overview and more detailed overview of all the ways the heated tip can be used. And in the next slides, I'll show you some examples of thermal material conversion, for example, which was done using the heatable tip. In this example here, the NanoFrazor heated tip was used for the local thermal reduction of graphene oxide. In this way, the tip could pattern regions down to 12 nanometers in width that are up to 4 times or 4 orders of magnitude more conductive than pristine graphene oxide. In the second example, the heated NanoFrazor tip as well as light from the laser writer head were used together to directly induce controlled and localized changes in the magnetic landscape of thin films. If you'd like to learn more about these methods in particular, then you could watch the NanoFrazor webinar by Professor Eduardo Albisetti and get more details. Thermal material conversion with the heated tip was also applied to other bioengineering applications, for example, for direct enzyme patterning, quenching supramolecular polymers, and also creating protein gradients. Another way you could use the heated tip is for thermomechanical nanocutting. And this is very useful because typically it's very difficult to structure 2D materials using conventional lithography, as this is often using aggressive chemicals or a charged electron or ion beam that could damage the material's properties itself. In these examples here, the heatable tip was used to apply localized heat and pressure, and in doing so, the tip could accurately cut into 2D materials and create the patterns that you can see in these images. How this was done is by applying the 2D material on top of a PPA layer. And when the heated tip is brought in contact with this 2D material, the PPA underneath was sublimating, which caused the top 2D material flake to break off in various shapes and forms. Aside from thermomechanical nanocutting, you could also perform thermomechanical nano-ironing of 2D materials. Here, the thermomechanical properties of the heated tip are used for nano-ironing of very thin films, and this technique was used in particular to reduce the impurities and defects on top of the 2D materials, which led to the boosting of their electrical transport performance and making them even more efficient for advanced applications like quantum computing. You could see the improvement in electrical transport exemplified in this graph here, going from the non-ironed 2D material flake at the bottom, represented by the gray data points, and going to the top nano-ironed devices, represented by the blue data points. If you'd like to hear more about how to improve the electrical performance of 2D materials through nano-ironing, I invite you to also watch the webinar of Dr. Lau, which will be available on YouTube. So, going back to the principle of the NanoFrazor, what is unique to our technology and what is also applicable to all the transfer methods I've mentioned before is the markerless overlay principle. And you could think of using this principle when you want to create more complex device application. And this is often required because we have to align pattern structures onto already existing structures on the sample. For example, when we have to add contacts to an already existing device. Now, if we're talking about nanowires or flakes and adding contacts onto those, this is particularly difficult when it comes to standard lithography techniques like photolithography or e-beam lithography, which use alignment markers for this purpose, because these materials can be randomly distributed on the substrate. However, with the NanoFrazor, we can overlay new patterns onto existing ones on the sample without any markers at all. And the way we do so is by roughly locating the region of interest where the nanowire or the flake could be located. We move to this region with our tip, and we launch the reading of the topography of this region in a damage-free way with the tip at room temperature. And in this way, very fine topographical features like nanowires or 2D flakes can be detected with a very high accuracy, even if they are buried under thick resists. For example, this is an indium antimonide nanowire that is only 70 nanometers in diameter, which is buried under a bilayer resist stack of 300 nanometers in total. Once we have the NanoFrazor topography image, the target pattern to be written can be directly dragged on top of the nanowire, and the patterning can be launched. In this example, you can see how we use a combination of thermal scanning probe lithography, or TSPL, to create the fine contacts, and then we can use the laser writing to create the electrode fan-outs and larger materials. This is an optical microscope image of the resulting device, and I'll show you here how this was exactly done with using the NanoFrazor. This is a screenshot of the NanoFrazor interface, and I'll launch this video. So as you can see, we can move the tip very accurately to the location of the nanowire, scan the nanowire with the tip in the cold mode, then drag and drop our design of choice, rotate it, move it in the way that we want, then launch the pattern. And this is a live view of the contacts that are written and the topography of these contacts overlaid on top of the nanowire. Using this technique, we were able to create much more complicated nanowire devices in a simple manner. You can see an example of this here with the writing of transistors on top of indium antimonide nanowires. In this case, we used a hybrid lithography technique, combining the capability of the laser writer head to write the source and drain contacts, and then the TSPL tip to write the very high resolution contacts on top of the nanowire. If you look at the scales, you'll see that the laser writer was used to write 250 by 250 micron contact pads, and the electrode fan fans out over 1 millimeter in area. This was a collaboration we did with the University of Minnesota, who supplied us with the nanowires. And we performed the patterning and the pattern transfer. You can see a side-by-side view of how this looks like after metallization and liftoff. And finally, the final SEM images of the fine contacts overlaid onto the nanowire. If you look closely, you'll notice that these contacts that were written with the NanoFrazor have near perfect alignment to the nanowire. And in this case, we achieved a gap of around 200 nanometers contact to contact. And this is quite impressive if you consider the large amount of metal which was deposited, in this case, 110 nanometers of metal. Once we finalized the devices, we sent them back to the University of Minnesota, who was able to electrically characterize these devices. You could see the resulting graphs here. And what they found is that we could achieve quasi-ballistic phase-coherent transport across this 200 nanometer gap. For more details, I invite you to check out our paper, which was published just this year. What I'd like to also mention is that this large area device was written within 1 hour, both for the TSPL and the laser writer. Now, this is an example of manual markerless overlay, but you could see how it could become tedious to repeat such an overlay if we had a very large area of structures onto which we wanted to overlay and pattern features. And this is why we've introduced an automated markerless overlay module onto our NanoFrazor system, and I'll give you examples of how this works here. So imagine we had an array of pillars, And on top of the pillars, we wanted to very accurately overlay such a cross. The way we would do so is as follows. We would need to do a manual alignment only in the beginning, and that is to the two opposite extremities of the nanowire array. And the way we do that is by scanning over these nanopillars at opposite ends of the array, and we do so to adjust the rotation on top of these nanopillars. Once this is done, we give the coordinates of all the remaining pillars, and we let the NanoFrazor tip move going from pillar to pillar, scanning the pillar, and then automatically aligning the cross or whatever feature there is to be written. You can see the resulting alignments here. With the automated overlay module, we can achieve routinely an overlay accuracy down to 25 nanometers. And if we tweak around our designs and our code, we can also push this further down to 5 nanometers alignment accuracy. This is different to if we had to manually move from pillar to pillar and rely solely on the stage accuracy for alignment. So I've shown you how we can handle the alignment and patterning of large area discrete features. How does this look like if we had a single large design that we need to split into smaller fields? So how do we handle large and complex layouts in a smarter manner? We do so by partnering with Genesis. And in this case, we used some of the existing importer features from the Genesis Beamer engine and implemented them in our own NanoFrazor software. And in doing so, we were able to create many different fields and field modes, for example, fixed fields, floating fields, and many different field types. And we're also able to order the fields that we want to write in a very simple way. And we need these functionalities because the way we perform our patterning is by using two different stages. So one is the piezoelectric stage, which has a range of about 50 by 50 micrometers. And the other is a coarse stage, which can move at any point in the 4-inch wafer area. So to perform high-resolution writing, we pattern with the piezo stage, and then the coarse stage moves to the next field, and we write again using the piezo stage in that other field. So if you think of importing a very large design, this is again going back to our nanowire quantum devices, you'll have many different regions in this design. Large contact pads, very large electrode fanouts, and also very fine contacts that need to be written rather with the heated tip. So what we can do in C2 with the NanoFrazor is simply import this large design. This can be a GDS file or a PNG. And we can locally draw a region of interest and tell the NanoFrazor that we want this isolated feature to be written with TSPL or the heated tip, and then assign all the other regions to the laser, for example. And we can also launch the patterning in the order that we want. So typically we start with the very high resolution features here. And then we can very simply tell the tool in which direction to continue the patterning using the laser and finalize the patterning as well. So this is how we tackle the importing of larger designs, but of course to perform such patterns, we also need to know a bit more about the endurance of the tip when it comes to writing very large areas. And for this reason, we launched a project to benchmark large area patterning with a single tip, and we used the MetaLens design as an example. You can see a glimpse of the MetaLens design here, and also a zoomed-in view of the smaller features that it's composed of. Here we're talking about rectangular elements that are medium resolution. They span between 100 and 250 nanometers in width, and they span a large area of about 700 by 700 micrometers. So in addition to patterning this large area metal lens with the heated tip, we also wanted to transfer this design and get close to creating a real functional device. The way we do so is going back to our high-resolution transfer methods, again using a high-resolution resist stack. In the first step, we launched the patterning on top of PPA, and then using a series of dry etching RIE steps, we transfer these patterns down to the silicon substrate. In this case, instead of depositing and lifting off a metal layer, we deposit 100 nanometers of silicon dioxide and lift it off. And it's these silicon dioxide disks that will act as a hard mask for the subsequent etching into silicon. In this particular example, we also use a special ICP RIE to perform the etching into silicon. This uses HBr chemistry and allows us to get very good straight sidewalls and smooth sidewalls. I'll show SEM pictures of the resulting features in the next slides as well. This is a side-by-side view of the entire metal lens. These are all optical images taken after PPA patterning, after the RIE etching into the resist stack, the position of the oxide hard mask liftoff, and finally after dry etching. If we look at snippets of the patterns, both as seen through the NanoFrazor system with this NanoFrazor generated topography image, and as seen through the SEM with the final generated silicon pillars, we see that these two images follow each other quite nicely. And we can also have a closer look at the finalized metal lens etched into silicon and the different parts of this metal lens. With this tilted view, you can also appreciate how the sidewalls of these individual elements are straight and smooth. And of course, this pattern transfer method, which took us from holes to rectangular features, can be applied to more high-resolution features. And we can apply this method to go from arrays of nanoholes to arrays of nanopillars. Using the same microfabrication steps, here we were able to achieve nanopillars that are 50 nanometers in diameter and 300 nanometers deep into silicon. So going back to our metal lens design, in order to achieve this large area 700 by 700 micrometer metal lens, we were doing the patterning over 34 hours, and we only replaced the cantilever once. So if you want to recreate this in a routine basis, you can imagine how patterning for 34 hours is not very practical. And this is why we've introduced our decapede module or multi-tip module. And with the decapede, we can use 10 cantilevers to pattern features in parallel, and this would reduce the patterning time of a metal lens down to 3.4 hours of patterning, for example. And if we can expect the same type of endurance from the decapede as well, then you can expect to write 5 of these metal lens designs before you need to change the cantilevers. Using such a multi-tip module allows us to expand our application space and renders our current applications much faster and much easier. And this is how we're tackling parallelization with the new NanoFrazor. It's through creating arrays of cantilevers that are all fabricated wafer level, similarly to the single tip, and also through packaging and interfacing of these cantilevers at the chip level. You could see how easy it is to remove and insert these PCB wired cantilever tips. It's much more practical now than in the case where we had to use tweezers to remove and insert the individual cantilevers in the past. We've also integrated newer electronics to our tools. Those are faster, lower noise, and much more scalable. When we put everything together, we get 10 tips writing in parallel. This is again a view of the NanoFrazor software. with the NanoFrazor optical microscope showing all 10 tips patterning onto a substrate. In this example, all 10 tips are replicating the exact same design. You'll soon recognize who that is. However, each tip is independently biased in terms of the reading and the writing, and also in terms of the feedback algorithm running in the background to correct the patterning. There we go. So this was one of the first examples we've generated using the decapite with all 10 tips patterning the exact same grayscale image on a thick PPA resist. Of course, what we're working on at the moment is having each tip operate independently, and this can be to create grayscale features, 2D features, or both simultaneously. And these 10 tips can also be working in combination with the laser writer head, all within one system, and again, using the same material substrates. With the new NanoFrazor, we have a lot more flexibility in terms of the modules we can integrate onto the system. So you could have the same base system working with a single tip, a decapite, and also a laser writer head in a very modular fashion. We also have many different configurations of the system, actually mainly 3, which you can see here. The first one is the tabletop version of the NanoFrazor, which occupies some of the smallest footprints. Or you could also have the standalone enclosure for the NanoFrazor, which reduces the outside noises. Or you could take the NanoFrazor system itself as a whole and place it inside a glove box and have it be part of a larger cluster of tools. You can check out our NanoFrazor configurator at nanofrazor.com, and here you'll have a very few questions to answer, telling us more about your research and desired applications. As an output, we can tell you which is the best configuration of NanoFrazor systems for you. Thank you again for joining this webinar, and let's make nano possible with the NanoFrazor. Before ending this talk, I'd like to remind you of the upcoming webinar series. We're excited to welcome many external speakers for our NanoFrazor webinar series. I list all of them here. We're ending the 2024 year with Professor El Bisetti and his talk on phase nanoengineering with the NanoFrazor. And then we'll launch the new year with a few talks on grayscale nanolithography, both for nanoelectronics and nanophotonics applications. Thank you again, and see you next time.